Hello, everybody. Welcome. Welcome to the webinar. My name is Andrew Jones. I'm the co-founder and executive director of Climate Interactive. I'm here with Ava De Leon, Chris Campbell, and others on our team. We're so excited. You're here for the big webinar on carbon capture and storage. As you're getting settled, please go into our polling software, polev.com. You can see, Ava, would you put the link? Look into chat. The link should be in there. Open another browser window to the site in the top left, or use the QR code. We're going to be doing some polling in here. It's really helpful. It's a good way. We are Climate Interactive, right? That's in our name. So we don't just lecture at you. We want to know where you are. There's someone in Germany. You got the idea. So please, someone out there, Great Lakes area, Mexico, and the US Southwest, in the US, the American West. Many in the US. Happy to see you here. South America. Is that Pakistan? The UK? And you can write it in chat. I see people writing in chat. And along the way, use the Q&A feature. We will be able to answer many of your questions. I see Catherine Markova from our team just joined. Use Q&A, use the chat, and engage that way. Oh, look at all these people. Love it. If you're just joining, I'm Andrew Jones. I'm the Executive Director of Climate Interactive. This is going to be about carbon capture and storage of 4 types: coal, gas, bioenergy, direct air capture. We're going to be using the En-ROADS simulator to dig into this issue. Right now, what you're doing, you're opening up another browser window. You're going to Polev, and you're letting us know where you are in the world. Maybe you're doing it in chat as well. So we're this team, Climate Interactive. We're a 16-person, not-for-profit climate tech company. We work closely with MIT Sloan and the Climate Pathways Project there. What do we see in the world? We see that there are some big gaps regarding the clarity that top decision makers have about the costs and the benefits of addressing climate change. They don't have the proper incentives to act, partly because they don't have the tools and understanding. And they don't have advocates around the world, like all that I see on this map, engaging effectively in ways that actually change the way that people think. What we found is that the interactive use of simulators actually changes what we call mental models. So we bring them to people ourselves. We give them away to you. Ava, can you put the link to our training program in there and let you go around the world to engage others about what's high leverage on climate and low leverage? We can't mess around right now, everybody. We have to put money into things that help the most and actually bend the curve on emissions. So many headwinds that we're going into right now. There's no messing around. How do we not mess around? We get grounded in the best available science. For us, that's using system dynamics models to help us test our thinking about what's really going to help and what's probably not going to help as much. So some people came to us and they said, hey, Climate Interactive, would you look at carbon capture and storage and see how much would it help? Not just abstractly or just reading other people's papers, but do the math on it. How much would it bring temperature down? How big is it going to grow? How much carbon dioxide gets captured? What are the other systemic effects if we have more of this technology? All right. Some more about our background. As I said, we work with MIT, and we have the hero of the week is Skook Jones, who led the creation of the CCS sector. Great job, Skook. He's one of us 16 here who's making this happen along with the rest of the team. This is a team effort. Where are we going? A little bit more on the motivation, simulation results. some of the mindset shifts that I want to offer, how you think about CCS and how it's going to help the climate, and then what really is going to help and how CCS might fit into that. And then we have some other improvements to share with you about fuel prices, about finally cement, steel, plastics, chemicals. Questions? Put them in the Q&A feature. We're going to handle many of them along the way. Why CCS? Well, the big reason is 3.3 degrees. We still think this is a reasonable baseline for where the world is headed by the end of the century. And now in En-ROADS, and actually I'll just do this. You can go, I'll share this scenario with you. We don't like the looks of the world that we would be headed to if we don't take much more significant, thoughtful, high leverage action. Here are two of the indicators. They're about 20. I'm going to copy this scenario. I'm going to go into chat and I'm going to post it so you can go in here and open up the model yourself. Here it is. Go open it up. We don't like the looks of a world with much more dengue and malaria exposure from warming, nor this kind of heat and humidity days. By the way, thank you, Probable Futures, for these amazing maps that now show us heat and humidity so we can see where we're headed. We don't like the looks of that. Why is this happening? Well, the biggest cause, of course, is the burning of coal, oil, and gas. Where are those emissions going? Coal and gas. I'll put over here. Here are the emissions. This is going to be the gas. Okay. Carbon dioxide emitted from gas and captured by CCS. There's none captured by CCS. It's not in our baseline. And here from coal. Okay. This is where things are headed, even with electrification, renewables, better storage, more energy efficiency. That's the trend that we think we're on right now. Can we address this? Of course, no big surprise. You know, well, the highest leverage way to address this, this is not a big spoiler alert. Many of you have seen this. What do we need? We need the clean energy revolution, energy efficiency and renewables, and electrification and other things that bend those down. We would also need direct pressure on coal, oil, and gas, and carbon pricing helps a lot. These are the things that directly address how much CO2 is being emitted from coal and gas by just burning less coal and gas. And we can explore, and there are many other webinars and many videos slowly doing what I just did. Right? That was, for a new user, that was way too fast. But the prompt here is, we know that needs to happen. And many people are asking, well, wait, how much can we capture? Can we still burn the coal and the gas and capture it on the way out of the flue? Like you're burning it leaves, that's carbon capture of coal and gas. Same with bioenergy and direct air capture as the last approach. I'll show you some pictures. Can we capture some of that? And I'm curious to see your thoughts on just what you think are some of those attitudes out there in the world. It gets talked about some. Actually, let me show you a few more. Yeah. Actually, let me go with the attitudes. Curious, another poll. So, how prevalent is this idea, do you think? Do you agree with this? Many people believe, this is people out in the world, that carbon capture and storage, if successful, like it works technically, we know if it grows, it might capture much of the carbon dioxide emitted by fossil fuels. Is this really a pervasive idea that's out there? Part of the work of modeling is to right size what we call our mental models. The model we make 99.9% of decisions with, the one between our ears. Should we take a lot of time to share the results from this computer model to help right size the mental simulation, the mental forecast? Do a lot of people believe this? What are you saying? 36, 37% somewhat agree that many people believe that CCS could capture much, I didn't define, but much. I'm kind of curious then, um, if it's much, and note, I haven't talked through what these are extensively yet, but I just want to get some of these attitudes that you see out there. So thank you. 35% somewhat agree, 13 strongly agree. And maybe just, we'll do the gas one in just a minute. Before I show the gas question, I'll ask you and just explain a little bit more. Particularly for people who are newer to this, what are we talking about? Gas or coal CCS, this captures carbon dioxide before it leaves the industrial facility. Okay? In industry or electricity generation, you're burning the coal. Some CO2 goes into the atmosphere, some gets captured and put underground. You pipe it, you put it mostly into saline aquifers. It's working at pilot sites. I was just looking around. Chevron has one in Australia for electricity generation, 4 megatons a year. That's very small. It was built in 2019. There's one for industrial use in fertilizer in Alberta, Canada. All of these are pretty small. Porthos in the Netherlands for industry. The Northern Lights in Norway, 1.5. And there's a bigger one planned by ExxonMobil. Okay, gas and coal. Bioenergy is going to have biomass, plants and trees that capture carbon out of the atmosphere, but then you burn it or process it into ethanol or other or electricity. Some goes into the atmosphere, some goes underground. It could be a net generator of emissions. It could be a remover. The dream, and there's some big dreams, is that it actually on net would pull a lot of carbon out of the atmosphere through this whole process. The third is direct air capture. And direct air capture is quite different in that it's pulling carbon straight from the atmosphere, like right in front of your face. Right in front of your face, there's carbon dioxide. What is it, 430 or so parts per million right here. In the atmosphere, it would pull it out with these big fans and chemicals, pipe it, shove it underground. And it's harder to do, and it takes a lot more energy, and it's more expensive because the carbon dioxide is so much less concentrated in the air around us. In coal, it's 15% carbon dioxide in the flue gas leaving, 15% carbon dioxide. Gas, it's 4%. In the air, it's 0.04%. 0.04. These are point numbers that I pulled from Joe Rome's excellent article about direct air capture. Ava, could you post that? Joe Rome at University of Pennsylvania wrote a really good article about it. So it's very diffuse in the atmosphere, so it uses a lot more energy. What do these things look like? Lots of pipes, lots of metal, lots of fans and machinery. Alabama, here's another one. Climeworks direct air capture facility in Switzerland, Louisiana. And then, of course, you have to have pipelines. Here's a pipeline for CCS that's being constructed in Australia. ExxonMobil has this infrastructure going from Texas in the southeast of the United States through Louisiana, some in Mississippi. You can see some are being used, those blue droplets are enhanced oil recovery. This is where we capture carbon out of, say, a gas-fired electricity utility plant, shove it underground in order to push up more oil. So we're not including that enhanced oil recovery here in this modeling. You can imagine if it's producing another fossil fuel by storing one on net, well, we don't know exactly how it plays out yet, but that's not what we're modeling when we talk about carbon capture and storage. Now, it's getting a lot of conversation. When I was in Dubai at the UNFCCC meetings, the president said the climate fight is lost without major carbon capture and storage investment. You probably have seen on your phones and in the world some of the advertisements. Clean carbon neutral coal, says Walker. Clean coal, now is the time. Shell, in the new energy future, will need to think the impossible is possible. Part of what we're going to do today is see what is possible and what really is impossible. Imagine capturing this much CO2 every day. Chevron ads, you've seen a lot of this. This was on my phone. Fuel your business, 90% fewer emissions. That's what's imagined to be possible in a single, I think, coal-fired power plant. It's about 80%, I believe, for a single gas-powered plant. Oh, if you put CCS on it, you could capture that much. Just more ads that are out there. Some of the consulting firms have gotten into it. Direct air capture belongs in every company's net zero plans, says Boston Consulting Group. And some of the potential, look at that number, 5 to 40 gigatons. So just lock those numbers in your head. 5 to 40, 5 to 40 for DACCS. We'll look at it a little later. Recently, some people are writing that here in the United States, under Trump, carbon capture sector is mulling rebrand and sees optimism. About to come online is a new big plant of direct air capture in Texas. Occidental and BlackRock has one. And there is a ExxonMobil is building a large gas plant with CCS just for data centers. Now, and as we know that there's a boost in energy demand because of artificial intelligence demands for energy. And this really prompts the question, and we're going to be looking at it. To what extent, if there's an existing power plant, does it make sense to put CCS on it? But the real question that we're addressing is, does that contribute to a global climate solution? Will it add up? Is this the start of something that will grow to be a significant contributor? And I'm going to show you why. The headline is, just because power could go out, and I want you to get the headline, is no. I think you're going to see how this industry is unlikely to grow to be a significant contributor to preventing climate change. And yet, at a project basis, may make sense because it is capturing some carbon out of facilities. So the opposite view was stated by Vicky Hullab here in the New York Times, who said, I care about our planet, I care about people that are impacted by climate change. And she said, she argues it will one day be possible to use oil and gas without producing planet warming emissions. Occidental is investing in some of these technologies. If we can deal with the emissions, we can continue to produce oil and gas. So there's the question that we can use the model to ask. Can we deal with enough of those emissions to continue to meet oil and gas and meet the goal at the top here, caring for the planet, caring for the people impacted by climate change? That's what we're going to be looking at today. All right. In parallel, we're thrilled there's so many people. I looked at the list of all your names before you arrived. So many serious users of En-ROADS who are out there. So many of what we call En-ROADS climate ambassadors. Ava, could you send the page of listing all the ambassadors? And if you are one of the people who's gone through all 63 training videos and run workshops, write your name and say where you are in the chat. Introduce yourself. These are people who can run a workshop like this for your business, for your community, for your government, for your family, whoever. So they're out there. Go check them out. Because you're out there, you want to know, hey, what do I do? Someone raises their hand when they're saying, you show them all these sliders at the bottom. Should we do things about renewables and energy efficiency and methane and ag and all these things? Someone raises their hand and said, hey, what about carbon capture and storage? So I'm going to show you how to simulate it in En-ROADS. And I'm also going to show you what we're learning from our analysis using this global model. We're going to do it around gas. And I want to focus on gas CCS just as the first example. And I'd like you to imagine, I'm going to go under here. This is where the test is going to live. We can subsidize carbon capture and storage, the subsidy for gas, dollars per ton CO2. Here in the United States, the Inflation Reduction Act, one part of it is called 45Q, and it offered $85 per ton of coal or gas CO2 captured by CCS. $85 a ton. Now, it might get it might get cut out of the bill. But the experiment here in this global model will be, what if that was around the world? And we talk about the United States. United States is 11% of greenhouse gas emissions. So this is mostly about the rest of the world outside of the US and Europe. And a lot of the growth, of course, is China, India, Indonesia, Brazil, South Africa, Turkey, Mexico, many of these fast growing emitting countries that are part of and have the opportunity to cut emissions of coal in brown and oil on top of it. They're in red and gases in blue, renewables expanding here, bioenergy, nuclear. Also in this baseline, of course, we have other sources. Methane's going to be in here, and that's relevant. Gas produces methane. So imagine, though, that I'm going to give a $85 a ton subsidy all around the world. Imagine then this is and it works. So we're going to assume that the technology works. My question to you all is, how much do you think, what percent of total natural gas emissions under that scenario would carbon capture and storage capture by 2050 in the more to most optimistic forecast? In case I am going to say $85 a ton. So imagine that it's being subsidized. And no, you do have to subsidize it. It isn't making a product that people can purchase. So it's going to be paid for with policy that says it must be done, carbon pricing, and or a direct subsidy for it. And that's a really key distinction, that it's got to be paid for. It's more like trash collection, right? It's cleaning up stuff that we don't want than subsidizing a new industry. Okay, so here we go. A good number of you have voted. Keep voting. And you'll note with the simulator, we ask you to run your mental model before the computer model. So what's your sense, do you think, of how much? A lot of you have voted. I want to see how we doing. 10%, 30%, gets 36%, 50%, and 70%. Interesting. Okay. Most people think it's around 10. Others 30, 50, 70. Now, informally, sometimes when I talk with people, I get some votes up around the 70s because that's what one facility might be able to do. Of course, across the industry, let's go see. 50% are say it's around 10. Let's go try it. Okay, good guesses. How do you simulate it here? Go to primary energy demand and primary energy. First, we're just going to ask, how big does this industry grow? We're not going to look at the carbon implications, just the industry growth. And we're going to see how much of the emissions. And here we can see under primary energy demand types, natural gas primary energy demand. And this is going to show where are we using natural gas. Fuel and electricity. Fuel is darker, for electricity is there. And in particular, you can see where it's being used. The fuel is mostly in buildings, transport, and some in industry. Well, yeah, and then electricity is over here, electricity generation. That's the distinction. electricity generation and the fuels over on this side. Let's go test it. Here we were. We're going to watch the growth. What did I say I was going to do? Under here. And the real simple question, someone raises their hand and says, hey, how much CCS? Show them these two. Make a subsidy. 85 is a reasonable one. And here it comes. Hit the tab, and then it grows. And note, in here, it's growing fast. I think that's 10 to 12% a year. So once it gets going, it grows fast. It takes a while to get going. The key thing is it's growing from almost nothing. It is so tiny right now. And you don't just immediately like take all the infrastructure that's being used in the world and kind of upgrade it like it's a software update or something. It doesn't just show up. This is an industry that's growing from being tiny. What is it out here? 0.7. Then it's going to double once by 2034 or so. And then it's going to double again, 2039, and double again. So it's growing steadily and fairly fast. However, it's not making a big wedge into the yellow area of electricity use of natural gas or fuel use yet. But it is, what you're seeing is a small wedge. It's small because the natural gas industry is so incredibly large already. So it's breaking in there and making a small dent into overall natural gas usage. Why is it a relatively small dent? Several reasons. Here we were with how we use natural gas in the world. Well, you can see as we add in how much of natural gas infrastructure is appropriate for carbon capture and storage. Look at the gray areas. So what is that? That's like 90% in the gas area over on the left, oh, excuse me, on the electricity area, and something like 80% in the bottom right in industry. Excuse me, 90 in electricity, 80 in industry. Can't touch the buildings. It's too small an application. Not in transport, not in some of industry, not in some of electricity. Now you see assumptions like this. This is such a brand new field that our researchers like Skook Jones were not able to go to the literature to see what are the main sources for how big this could, like how much of the percentage it could cover. You've got to go make some things, make best educated guesses on some numbers. When we do that, we make these assumptions changeable. So if you didn't like those assumptions, here they are. CCS potential, electricity generation, and in industry, maybe they're higher and we would see more growth. See the blue line change? Maybe they're higher. That would lead to a little bit more growth. And there's some other assumptions that we're going to change later. But the second reason, the first reason of why it doesn't help much is it takes time for this industry to grow, even when it's growing aggressively. Secondly, it's only applicable to a certain percentage of the overall infrastructure. The third is that it is expensive. Let's go look and see what it costs. Financial cost of CCS, we said 85 a ton. The price we have here is about 90. So 80 is going to get some of the market share, but it's a good bit, $85 a ton. And note that when you spend that money, you can go calculate how much money we're talking about spending. By 2060, $50 billion a year to pay for it. Now, and note, this is something that will require steady payment. It's not subsidized early on and then it kind of goes on its own. It will always need policy or payment, like trash collection in a city or anywhere in a residential. So that's how much it will cost. And the surprise for me was how little that blue line falls. We have explicitly modeled the economies of scale learning curve. That is, you build some capacity, and every time the capacity doubles, we get a drop in the cost because of production efficiency and economies of scale. It is only dropping 5% per doubling. That is a progress ratio of 0.95. You can change it. You can see it down here. Why is it 0.95 and not 0.8, which is what we had for wind and solar? Some are arguing that actually it should drop, say, like wind and solar have dropped over the last 35 years. Here's solar's drop in costs over time with a very aggressive progress ratio, 0.8. Now, note, you need two things for the price to drop. You need a kind of generous progress ratio, and you need a lot of production in order to get as many trips around that reinforcing loop as possible to bring the cost down. So what's happening on the left is neither. You're getting a small progress ratio and not enough growth for the industry price to really drop a lot. Now, maybe it's different and could be faster. I'm going to change it here and we can see, hey, maybe it is going to be more, and we could explore the implications of that. But why is it so different from wind and solar? Our team found an interesting diagram that explained it quite clearly. On the left, you see design complexity going from simple, like solar PV down up here, to much more complex. In this case, carbon capture and storage has a high degree of design complexity. On the x-axis is the need for customization. Coal-fired power plants, electricity generation, plastics and chemicals, and all the things that use natural gas out there, or those industrial facilities require a large degree of customization. Mid-level, you can see carbon capture and storage up here. With bioenergy, it's high in both accounts. This is a 5% gain for every doubling. Down here is a 20% gain in the bottom left. High complexity, high customization is leading it to be a low progress ratio. And it really, one way to think of it is these are the things that drive this learning curve. And at the best, with new technologies, it's like the subsidy gets it going, and then the learning rate is what gets the snowball really rolling down the hill, as we've seen with wind and solar over the last 20 years. However, what you have is a much more gentle slope and also a long-term dependence on subsidies. CCS doesn't produce a product that can be sold that brings revenue and profits that get reinvested to drive more reinforcing loops. So here we're seeing a modest contribution. So what does it do for the climate? And I'll show you, I'm going to go back to where we were before, and I'm going to pull up another key graph. If you're going to present this to people, this is a great one. Go to CO2 emissions and then scroll down here to that first graph I showed you. CO2 emitted from gas and captured by CCS. I'm going to hit forward again to redo, and we're going to see that $85 a ton around the world. What do you see? You see that black line? That was where we started. The gray area is the total gas CO2 emitted in the world. The blue is how much is being captured by CCS. So that is the sliver that I gotta say, just disappointingly, I want it to be more because it would be great. The best analogy we have is sulfur dioxide and nitrous oxide, another pollutant. The acid rain concern that drove many when I was studying environmental science, that was a big issue. Sulfur dioxide and nitrous oxide scrubbers have been added to what, 80, 90% here in the US of electricity generation from coal. And it can capture a lot. But it seems that the carbon dioxide, given the assumptions I just laid out, is unlikely to capture a large wedge globally. Now, on a single project, perhaps, and it can help. And so don't count it out. If there is a coal-fired power plant or a electricity generation from gas, don't count it out for that. But here, we're not seeing it add up to a significant solution. Clara Iglesias on our team did some math. And to answer your question, remember where we were before? We were saying what percentage? This is what you said. What total percent? 51% of you said around 10, 30, 36% said about 30, 50. The answer from that wedge right there, what is the answer? This little area right here is 6%, and it's that area. And by the way, if you want to replicate this and do the math, do what Clara did. Go here, copy data to clipboard, and then you can go and replicate this, because all the data and all the outputs, you can just put in a clipboard and then copy into Excel and do your own math. But it's about 6%. 6%. So you were right. More than half of you were right. About 6% at $85 a ton. We thought we'd push it and say, well, what about if it was doubled? And what if it was higher? What was it about 170, 170? And here it's about 12%. So in that range of 6 to 12%. That's not nothing, but it is not a significant contributor. And importantly, and we could put it together with other technologies in a minute, but the thing you've got to come back to is this idea. If we can deal with the emissions, we can continue to produce oil and gas. And what we're seeing is it is unlikely, given the assumptions we just laid out, and our modeling suggests that it's unlikely that we could grow an industry that could capture a significant amount, at least, of these gas emissions. I hope you just saw also another surprise. Did you notice something that happened in this last move as I upped the subsidy to 170? Wait, what's going on here? Look in the bottom right. Wait, what? More natural gas. When we start getting these major subsidies, that is injecting money into the overall industry, that is changing the economics of production and fuel usage in the industry, that is not just boosting CCS. You see, it's important that the light blue area is growing, but we're getting this kind of compensating feedback, kind of like a rebound effect of sorts, where actually we're getting more usage of natural gas overall than we had before. More natural gas. Well, what else comes with that? Well, what else comes with that is a little bit more. It's not huge, but look at the blue line. At a time when we need methane going down, methane is going up a little bit more. There are some other challenges, and I'm going to do the same thing with coal. Let's go try it with coal. Well, we're going to add that in and look at the same graph. Well, what about coal? Because coal is so carbon dense, it's probably the smartest use of CCS. Do it first. Now, one note, what did coal do in this scenario that I just did where we had gas CCS? There's a little bit less coal. Why? Because we have more gas. The gas is pushing out coal. So it's being reduced. I'm going to subsidize gas CCS, coal CCS a little bit. But I'd like you to think about system-wide impacts. I'd like you to join me in being a systems thinker about this. What would happen to air quality and health if we subsidized coal CCS? Go to the poll. What are the air quality and health implications of more subsidized coal-based CCS? What would happen with more coal? Bad. There's 3 letters. Worse health. Why worse health? Why asthma? Why more deaths? Play out the causal thing in the energy system. Worse health. Why? More pollution. Again, what's going on? Higher PM 2.5, worsening of air quality, more deaths Yes. Someone write in there, what is the causal chain? You have more CCS. Why is it having all of these impacts that you're right, that you're correct about? We'll go look at it. More coal dust, more deaths. Exactly. Let's go look. More PM 2.5 in the air particle. Let's go look. So here we are. We're going to subsidize it. I'm just going to boost it up. It has the same effect. You're capturing some. You're putting money into the industry that's changing it to more coal to be used. You're going to have more coal. Let's see. And so what did I say we're going to go look at? Well, let's just see. More coal. There's the coal. More coal. If there's more coal, what happens to impacts air pollution, PM 2.5 up? Note, on its own, if this is not adding up to be a solution, and in fact, it's creating other challenges in the world. So, and note, we can go look and see similar impacts with bioenergy and BECCS. That's a whole nother, we're going to do a whole nother webinar on that. What then do we need to be doing? And where might CCS actually fit in some way? It's so much in a base case scenario, it doesn't do very much. What should we be doing around the world? So I'm going to ask, uh, let me, so what do we need to do? And then we're going to explore how CCS might contribute. What do we need to do? Encourage renewables, carbon pricing, removing subsidies from fossil fuels, encourage nuclear, phase out fossil fuels, set a carbon price, energy efficiency, electrify, afforestation, deforestation, reducing methane and other gases. Well said. Look at all these votes. Improve food systems, energy efficiency, discourage wood-based bioenergy. Let's go look. Okay, here we are. And this scenario, I think where I have, maybe I'll share this one with you as well, so you can see it. I'm going to copy this scenario link, and I'm going to drop it into chat right here. Drop it into chat. You've said what else needs to be done, but I want to show you a few other things just to push on with this scenario. You show me what needs to be done. I'm going to show that in a minute, but I want to just help you see other things that can be explored in this scenario. Some others, I showed it a little bit early on. How much, well, won't do the money. We're going to do the transport capacity. This is pipelines, etc. How many trillion cubic meters per year? This dotted line is the size of the natural gas industry globally. We'd be building up by 2100, kind of where it was 10 years ago globally. Now, the key thing is, this is for a product that you're not shipping it somewhere where someone wants to buy it and give you money. This is for trash disposal, basically. But that's the pipeline capacity. We also modeled, the team looked at the storage that's needed. How much is stored underground? The dotted line is what people estimate is available, mostly saline aquifers. And we can see that even at this scale, it's not likely to push up against those limits. I thought maybe that would be one of the limits, right? Where do you put all this stuff? Turns out it seems that there's abundant storage area. That is not one of the big limiters overall. We can go look at how much would be spent. We can look at the assumptions. And about storage, there are other factors that we can look at that we should test. As I said, there are a lot of assumptions. We don't know about leakage, and many people talk. we're putting it underground. Will it really stay there? And there's a study that says it could be assumed. The IPCC AR6 said assume the loss to be zero, leak rate zero. There's the study from the IPCC. But what if it's higher? And you can see, well, what happens if you capture it and it leaks, how much less there is. So it's pretty important to think of that as a consideration. But the key thing is when there's considerations like that, we don't want to just say, oh, it could leak, forget it. No, let's quantify it. How big a deal is it? How much does it matter? We like to do real-time sensitivity testing. Other factors that are here in the growth of these two industries, here they are growing very fast around the world. They are affected by many other factors like the capture effectiveness. Well, that would really affect how much. I'm going to go look at this again. The capture effectiveness could be higher. It could be lower. That's going to affect how the system works. The progress ratio could be better, and that would lead it to grow more potential. There are a bunch of other factors that would be very important. Okay, those are some of the things you can go look at in the simulator. But that's not where we were. We were looking at the big list of all the things that you were saying to do. Let's go look at it again. What was it? It was all of this, and then we're going to add CCS and see how it can be part of it. Let's go try it. You said renewable energy. The clean energy revolution is helping so much. If we get breakthroughs with hydrogen and other kinds of storage, then it can help more. If we electrify, we can use more of that wind and solar and zero carbon energy, down to 3.1. If we have energy efficiency in transport and in buildings, 2.8. Pressure directly on coal and oil and gas because they're scissors. The clean energy revolution cuts emissions. Direct pressure on the source itself is the other half of the scissors. Those two together could work well. You also voted for carbon pricing. This could help a good bit as well. Other sources of greenhouse gases, methane in agriculture, better agricultural practices for animals, for crops, waste and leakage. We're down at 2.1, cutting and reducing deforestation, 1.9. Okay, these are many of the things that you suggested. Oh, I want to get food under here. Someone else said that. It's a little buried. Food from animals, food waste. Someone voted for these things, but we're at 1.9. Now, let's go look at this world for these emissions that we were talking about and what's going on. Think, what's going on with CCS in this world? If we had $139 carbon price in this what if scenario, CO2 emissions, coal, CO2 emissions from gas. See the blue areas. We are getting some CCS. Why? Because it is incentivizing the role of CCS. It is providing a revenue source, and it takes a lot of revenue, as you know, to pay for it, to complement this scenario with a significant reduction of coal and gas. To get to 1.9, it is insufficient to count on CCS. It is necessary to significantly reduce coal, oil, and gas emissions, and possibly CCS could supplement in some way. In fact, in this scenario, out by 2080, what is it? It is, I don't know, capturing 20%, 30, not 30% of the overall emissions here, but that's close to 40% of those coal emissions out in this scenario. And I don't think we've even subsidized it here. No, that's just from the carbon price. So in this world, if we were serious about meeting these goals of getting down well below 2 degrees and spent some money on the gas CCS, see the wedge for blue grew, and coal CCS, watch there, the coal CCS wedge grew. What is that? That's more than 50% is being captured. And then it brings it down some more. The other possibility is, I hadn't talked about it yet, but direct air capture. Again, pulling it from the air, it is much more expensive. You can go see the price down here. It is around $1,000, or no, $650 a ton. Let's go incentivize it. Some people are spending money on carbon offsets. That money is going into, in some cases, direct air capture. But imagine if it was spent at $1,000 a ton, like very high. Notice what's the first thing to do? The cost goes up initially. How could that happen? Why would costs go up initially? It's so energy intensive that it's increasing the cost of energy around the world because of that increased energy demand. And that large part of the $1,000 a ton that goes to energy is making it more expensive before the learning curve kicks in and brings it down. So if we had it in this scenario, what do we get? 1.5 gigatons a year. 1.5 gigatons a year. I'm going to remind you of some numbers. Do you remember that BCG study that said it should be part of every net zero scenario? We could get 5 to 40. We're seeing here with these high costs and the inability to bring the cost down a lot, 1 to 1.5 might be a lot. This is, where was that? That was this BCG study that said maybe 5 to 40 gigatons a year. More in the realm of possibility came out of the Shell Sky scenario. Shell Sky, excuse me, they used to call it Shell Sky scenario. Shell Horizon is the new name of this scenario. This is really recent. What they imagine for CO2 removal, see, the blue is DACCS. By 2080, it's about 4 in their scenario, what they imagine. 4 gigatons per year removed. 4. Now, again, we don't have the we're not here to forecast the future of DACCS. We're here to provide a tool to test the implications of a set of assumptions for it with pretty reasonable and good research and behind it, but we're open to different scenarios and different assumptions. So if the industry is a good bit bigger, and note, we calibrated this against the International Energy Agency's World Energy Outlook. But if it was higher and it was going to be bigger, we said, what was it, 3 or 4 perhaps? Maybe the industry will be bigger. And if so, then we get to go see what would happen to overall costs and go look at overall greenhouse gas net emissions. This would get us down to 1.8. So the key thing you just saw there, if we can succeed at getting coal, oil, gas, methane, deforestation emissions, F-gases, nitrous oxide emissions down to below 2 degrees, 1.9, another 1.8 could be these kinds of actions. Do you see how it could supplement, perhaps augment what is being done in the world? However, when it comes to priorities for what really does the serious work of getting us to well below 2 degrees, we have to talk about priorities. And the priorities, as you saw, were things in the clean energy revolution, in addressing fossil fuels directly, in addressing methane and F-gases and nitrous oxide and deforestation in forestry and agriculture and waste and in many of these other sectors, and all the things together that get those emissions down. And CCS could be something that could bring us a little closer to the goals. You'll hear advocates saying, and IPCC study says we need CCS. That's in the framing of to get to 1.5. It is another one of those 0.1 degrees that could get us there. However, it isn't the top priority. And it's a little bit like talking about just things like CCS or some of these other measures without serious policies on mitigation feels to me a little bit like going to a doctor with a smoking problem and you're smoking and you have cardiovascular and asthma and lung problems and the doctor says, yeah, I want you to focus on diet, exercise, yoga, and doesn't say stop smoking. The stop smoking, of course, is reducing the emissions from coal, oil, gas, methane, deforestation, those areas. Those are the top priorities. Now, along the way, there's some shifts that we've noticed in thinking that we think are particularly critical. And we think these are the deeper ideas to take away. Not as much just the calculations, although go play with the model, show the model with people, 21 languages. These are some of the mindsets, and we're curious about your thoughts of this is the first time we've ever shared these publicly. It when we think about a large global CCS contribution to addressing climate, not project based. This is more, is it a big solution around the world? It's been talked about with overly optimistic language, as if it's like applying technology to a facility. I've heard people say, oh, it can capture 80% of a facility emissions. So shouldn't it capture 80% of industry emissions? I just showed you why that's not the case. It's more realistic to think about growing an industry over time from close to zero. That's different from, say, I don't know, it's talked about like a software upgrade, like your computer just gets an upgrade, as if we could take the gas and coal infrastructure and very quickly engineer this fix to all of it. Also, it gets talked about as if it's like selling a product. Shouldn't it be like wind and solar? Well, no, it's more like paying for trash pickup. We have this stuff that nobody wants. You got to go pay for it to get rid of it. And we should. It often is talked about the subsidies would just launch this industry. The subsidies would not just launch it and then it would be on its own. Instead, it would need to be with policy or payment and subsidies forever. Also, the learning curve would be like wind and solar. No, it's got a high complexity and customization, so it's very different. And last, that we could imagine this problem, and Vicky Hullab saying perhaps we can just keep burning coal, oil, and gas if it had coverage like NOx and SOx, well, then maybe, but no, it's more in that range of 5 to 10%, unless we cut coal, oil, and gas, and then it could capture a bigger percentage of the overall emissions. Okay, boy, I've taken you through a lot in this journey. I've taken you through a lot. Overall, what are we seeing here? What we're seeing is it's time to get serious about prioritizing high leverage actions. We're not wasting time on lower leverage actions around the world. How do we share these insights? We can't just say these things. We have to engage people to think on their own terms. We're offering a simulator here. En-ROADS, there's a training course. It's freely available online. Ava, post the training course again, would you? And would allow you to go engage people. First, engage yourself. Go test these assumptions. Think about it. Go check out the explainer. Ava, would you post that link to the gas and coal CCS explainer, or the gas one, and then the DACCS? There's a video that's 10 minutes long that just shows you the basics of how to use the model. But then we're also seeing that while CCS may be useful at a facility scale, from our analysis, it seems with a reasonable set of assumptions, unlikely to be able to scale to be a significant contributor to preventing climate change. and is thus a lower priority, possibly the one that, if it attracted significant funding, could pull from higher priority areas, although that wasn't in the model. So keep your eyes on the prize, my friends. The stakes are high. We're not here to mess around. We have to do all we can to create equitable futures by addressing this big challenge and directing our resources where it matters the most. Engaging leaders to do it isn't going to be easy. It's going to be worth it. Go get them, everybody. Bye-bye.